and thank you for the opportunity to talk here today. So I will be talking about certain sets of hyperbolic polynomials and describe how they kind of look like a variation of polytopes, which I will call soused polytopes. Specifically, I'll be talking about univariate hyperbolic polynomials. So that is univariate polynomials with real coefficients and real roots. And the sets are the sets with hyperbolic polynomials that share the same first few coefficients. I'll start by going into why the origin of my interest in these sets. Describe some of the main properties and their similarities with the polytopes. And lastly, this perspective of thinking of them as polytopes will give us a way to determine which root arrangements can occur in these sets. So yeah, my interest in this stems from proof by Arne Lien of the following theorem called the Timoftes degree principle. You may have seen it before. It's just if you have a symmetric polynomial in the variables and of degree s, then it has a real zero if and only if it has a real zero with at most s distinct coordinates. So it's a dimension reduction for symmetric polynomials, essentially. I'll start by just going through some of the main ideas for Arne's proof of this. And it's okay if you don't get that part. It's just to show that it's not such an arbitrary set to study. So the first, the main idea behind this proof is that you identify the orbit space of Rd with respect to the symmetric group with a set of monic hyperbolic polynomials of degree d. To see that, then let f be a hyperbolic polynomial. Then you can express its coefficients as the elementary symmetric polynomials evaluated at A, where A is the tuple of zeros of f. So to see that, you can just see that the first term of f comes from choosing a t from each parenthesis. Then you get the first term. Second term, you get from choosing a t from each parenthesis except one. And you have d many, so you sum them together and you get the first elementary symmetric polynomial. So that's kind of the main idea behind the proof, which goes as follows. Since f is symmetric, we can express it as a polynomial in terms of the elementary symmetric polynomials. And since it's of degree s, we just need the first s few elementary symmetric polynomials, because the rest have too high a degree. And then f being 0 at a is equivalent to the polynomial p at alpha 1 to alpha s being 0, where alpha 1 and alpha s is obtained by evaluation of these elementary symmetric polynomials. In other words, f has a real zero if and only if these sets of equations have a solution. So you're taking essentially the orbit space and you're just slicing it down by fixing the first s coordinates to be alpha 1 up to alpha s. So if this intersection is non-empty, then you have a 0. That's kind of the main step. The last step is to show that in these sets you always have a point with at most s distinct coordinates. that's kind of the proof. Yeah, if you node it off during that, that's fine. Now you can start fresh. We define the following sets. We start with a hyperbolic polynomial set, and we look at the set of all the other hyperbolic polynomials with the same first few s+1 coefficients. So that's, like we saw on the last page, that is the same as fixing the first coordinates in the orbit space, essentially.
Do you fix the degree here, or do you let them be of any degree?
Well, since you're fixing the first coefficients, you're also fixing the degree. So every point, if you start off with that having a 1 as alpha 0, each also has.
Oh, I see. The first view is starting with t to the d, not starting with 1. Okay,
so
I understand.
Yeah, you fix the degree.
Okay.
Yeah, so Konstanz proof, he made the following observations. That is, if you fix at least the first 3 coefficients, so s being 2, and I usually denote s by the, you kind of always, work with money polynomials. So let s be 2, then it's first 3. Just, yeah. So you made the observation that if you fix the first 3 coefficients or more, then you get a compact set. And since the compact set has extremal points, you identified that all the extremal points consist of polynomials with at most s distinct roots. So that kind of finishes the proof I was talking about. And yeah, the extremal points are the polynomials that cannot be expressed as a convex combination of some other polynomials in the set. So these are some quite nice properties. We're gonna look at some others. And we can take an example first, I think. So here we have some 4th degree polynomial with the roots you can see 2, 1, -1, and -2. And we let s be equal to 2. Then if you take any polynomial in the set h2f, it has the same first 3 coefficients as f. So there's 2 coefficients that are free, that are left over. You can just map those coefficients to a point in R2. And that is the picture I just see here. It's just this mapping. Forgot to say, but if anything is unclear, it's just to interject whenever it's fun. So in this case, you see F is the red dot in the middle. You also see that it has 3 extremal points, these blue dots. These correspond to polynomials with 2 distinct roots. We can also check that the green curve segments, they correspond to polynomials with 3 distinct roots. And the interior, that's the polynomials with no repeated roots. And yeah, just a note on the name star polytope, which may have seemed a bit odd. So in this example, it kind of looks like a triangle, except it's your pet triangle, and you haven't fed it enough for a while, so it starts looking more concave. So that's where the name comes from. But we'll get more into why it's okay to think of it as a polytope and a star version. I mean, it's not convex, but apart from that, many things will be similar to polytopes. So let's look at what we can say about these sets in general. Kostov had an article where he showed that these sets are always contractible. So that means it's continuously deformable to a point. We can also show what we observed in the example, that first you can show that it's either full dimensional, so of dimension d minus s. These are the number of not fixed coefficients we have, or else it's a point. So it's one of the other. And you can show that if it is full dimensional, then as we saw, the interior consists of the polynomials with no repeated roots. And the set is equal to the closure of its interior. So it's a fairly nice set. It's compact, contractible, closure of its interior. It's a very well-behaved set. So I want to say something about the star part of star polytope before going into the polytope part of it. Sure.
Yeah. So if S is less than the degree, can this set still be one less 1 point?
Yeah. Yeah. Actually, in the example we had. Okay. So in this example, we started up with a degree 4 polynomial. And then there are two things that can occur. Either you get this set, or like a variation on this set, or you get just 1 point, which corresponds to if you start with a polynomial with just one root. I see. Yeah. So this happens. Yeah. So I note on the star part, let's start off with a set which is at least 2-dimensional. Then we have a full dimensional, so d minus s dimensional set. And Chevalier showed that at the generic point of the boundary is concave towards the interior. So, like in the example we saw. Generic in this case just means a polynomial with one double root and the rest simple roots. This was generalized later by Megueritian, but in simpler language we can say that if you take a polynomial in the set which has at least s plus 1 distinct roots, then they can be written as a convex combination of interior points. So remember that the extremal points, they have at most s distinct roots. So these are just everything else. So, yeah. So now to the polytope part of the name. We wanna describe these sets as analogous to polytopes. So since you can describe a polytope by how it's built up based on spaces, 0, 1, 2, 3-dimensional spaces and so on. We're gonna try to give a good definition of a face, and for that we need notion of a root arrangement, which I will call a composition. So suppose you have a polynomial f with distinct roots a1 up to al, ordered increasingly, and the multiplicities of ai is ui. Then the composition of f is just a tuple u1 up to ul. So it's like a partition, but it's kind of a permutation of a partition. The parts sum up to d, but it's ordered according to the roots, not the size of the multiplicities. Quick example. Here we have some polynomial f with roots -4, -2, and 3. with multiplicities 2, 1, and 3, respectively. And the composition is 2, 1, 3. That's it. So since we want to construct bases, we also need a partial order to go with this. So we start with an example. We want to say that the composition 2, 1, 3 is greater than the composition 3, 3. Because if you just put a plus sign in between 2 and 1, we get the composition of 3, 3. But we don't want to say that 2, 1, 3 is comparable with 1, 5, even though if you add 2 and 3 together, you can get 1, 5. So we want them to be in next to each other. So in general, we say U is greater than V if we can obtain V from U by just replacing commas with plus signs. That's it.
So this is like dominant order for partitions itself. You don't list them and
what was the order?
So this ordering is like a dominant order for partitions, right? Except you don't list them in the you don't list them ordered like partitions. You kind of you do it in the order.
It's not the same, but I mean, if you turn the dominance order upside down, you get something similar, but it's not.
Yeah, I understand. It's not that because you don't list them in the order in the.
Yeah. No, but even if you were to sort of quotient out the permutations of a composition and get partitions, the corresponding induced partial order, I think, is not the same.
It's not okay. Okay.
I think so. Yeah. But it shares many properties.
Okay.
I think I don't remember hyperboles, but it maybe dominance implies this. I think it's one. But this is a nice partial order. It gives the set of compositions of D the structure of a lattice. So anyone who doesn't know what a lattice is, if you have two compositions, there exists a so-called join of these two compositions. That's a minimum composition which is greater than both of them. Similarly, there exists a unique meet, which is a maximum composition which is smaller than both of them. Which is a nice property we will be needing. Yeah, so now we are in a position to construct bases. We'll define them as the subsets of HSF, which, so for a composition U, we take all the polynomials in our set, which has a corresponding composition less than or equal to U. So we're just closing it down, essentially. So in particular, the composition 1, 1, 1 is greater than every other composition. You can just put the appropriate plus signs wherever, and it gives you your composition. So the corresponding base is the whole set, which tracks with what we want. Let's look at an example. In this case, we have a degree 5 polynomial, so you see below, and we let S be equal to 2 again. Then in the leftmost picture, we can see these 4 external parts, and the corresponding composition is written next to them. So these have all 2 distinct groups, which we knew from accordion, but this was going to be the case. In the middle picture, you see these curve segments, the green ones. They have all 3 distinct groups. And in the right one, we don't see it, but there's 4 two-dimensional faces as well, which we know to be concave towards the interior, and the corresponding composition.
So these are all three-dimensional pictures, right? And supposed to kind of see a simplex.
Yeah.
Or star
Exactly.
simplex.
Yeah. So let's see if that tracks with our definition of types. So if we take the composition 311, you see it has this curve segment has two endpoints with corresponding composition 3, 2, and 4, 1. And 4, 1 we get from 3, 1 by adding the 3 and 1. And 3, 2 we get by adding the 2 1s. So, so that works as we would like it to be. You can play a similar game for the others. If you look at the hazard diagram here, see for instance this 2, 1, 1, 1 composition is greater than these three compositions: 3, 1, 1, 2, 2, 1, and 2, 1, 2. And it's not greater than any other. So if you look at the picture again, you see that this two-dimensional thing, and it's corresponding boundary. These three green lines with composition 3, 1, 1, 2, 2, 1, and 2, 1, 2, just as we would like to. So it's something that we'll see works well in general. This is a good picture to have in mind. Let's see what we can say about these faces in general. Again, we have a theorem by Konstanz saying that these faces are either contractible or empty. So we didn't have the empty clause when we have this full set, HSF, because we started out with the hyperbolic polynomial. In this case, we didn't start off with a hyperbolic polynomial with composition U, so we can have empty sets. And this occurs. We can also generalize some other statements. So if we let L be the length of U, and the length is greater than S, then the corresponding face is either of dimension L minus S, or it's a point, just like in the normal case, but now it might also be empty. If the length is less than or equal to S, then you just have a point. So in particular, we have that extremal points have at most S distinct roots. So if we take all the compositions of length S, these are finite, and each face contains at most one point. So then we have finitely many external points. Yes. So finitely many polynomials with the most S distinct roots, finitely many external points. Similarly to the whole set, we have that if you have at least a one-dimensional face, then its relative interior consists of the polynomials with composition U. Just like the whole set had an interior which had as interior points polynomials with no repeated roots.
Is it? Do you know when the set is empty or not? Is that...
the faces?
Yes, exactly.
No.
And I guess my second question, so is the combinatorics of the start polytope, are they exactly the same as the combinatorics of the actual polytope?
In a very similar way, we kind of get to that in the next slide.
Okay, sorry.
No, that's fine. But yeah, I would say it's, so as you saw in the picture, we started off with like a start simplex. And in general, you always, when you fix two, you either get a point or a start simplex. And what it looks like is that you essentially get what you would get if you started out with a simplex and sliced it down with affine hyperplanes corresponding to some specific rules, but the combinatorics is very much inherited from this starting point, this simplex. Yeah. The relative interior consists of the polynomials with composition U, and the face is also the closure of its relative interior. So it's also nice. There's no tentacles going up into somewhere else. Yeah, so this perspective with the faces is going to lead us to a way to determine which compositions occur. Actually, so that's kind of a partial answer to your question of this. So if you consider the case when you have a polytope, you can define it as the convex solve of its extremal points. So its faces are determined entirely by its extremal points. We're gonna introduce sort of an algorithm here, which does pretty much the same thing for our star polytopes. So we know the extremal points are at most S distinct roots. So suppose you start off with P1 to Pk, let them be all the polynomials with at most S distinct roots. And you take the corresponding compositions, P1 to Vk, and put them in a set. Then the first step is for all pairs of compositions V1 to Vk, you compute a join. So this was the minimal composition which is greater than both of them. So you do that computation for all pairs of vertices and you put them in a set, W. And then the next step is just to close up this set. So you take the set of compositions where each is greater than at least one composition from W. And then the set V union U is the set of all compositions that occurs. Yeah. If you start off with polynomials with at most S distinct roots, you can determine which faces are empty or not by this algorithm, essentially. So let's just go through this with our previous example. We had this picture. We let S be equal to 2. And we have 4 external points with compositions 4, 1, 2, 2, 3, and 1, 4. And then first we compute the joints of all of those pairs. So we have the join of 4, 1, and 3, 2 is 3, 1, 1. 4, 1, and 2, 3 is 2, 2, 1. You can double check it just by adding 2 and 3 together, and we have 4, 1, 2 and 1 together, and we have 2. And similarly for the rest. And step 2 is to close it up. You just take all the compositions of length 4 and 5 in this case, and W is. And then the compositions that occur are all the compositions of 5 of length at least 2, which is we can count and check. We have 4 vertices and 4 blue points. We have 6 compositions of length 3 and 6 green lines. And, yeah, similar for those. It's not always so nice. It's particularly nice when S is 2, but the algorithm still gives you the correct output. Yeah. So that went a bit faster than expected.
What if you do this directly to V? You get something nice.
If you do it directly to V, in general, this is fine. In general, you have polynomials with exactly as distinct roots as its vertices. And in that case, you can just go to step 2. But in some cases, you end up with extremal points which has fewer than s distinct roots. And then if you just jump to step 2, it's not true. Then you have to do step 1 first.
No, I mean, when you take this upward, how do you call it?
Upward closure.
Yes, upward closure directly to step V.
Yeah. In general, in the generic case, this will work. But there are examples where it doesn't.
In this
in this case, we could have done it.
Right?
In this case, we could have done it.
Okay.
Yeah. As you see, we have these are all the composition of length 2. So if we close it up, we will include all of the lengths. Yeah, I went a bit faster than expected, so thank you for listening. There's a pretty picture of Konstanz.
Thank you. Are there any other questions?
What's the meaning of those coefficients in the polynomial in the example? I mean, on slide 17.
The meaning of them?
Yeah, I mean, you just choose a particularly nice irrational number. Or...
Oh, you mean in the
I mean, why did you choose those?
Those roots. No, it was just the first example I chose very pretty roots, like -2, -1, 1, and 2. And I just wanted to show that that had nothing to do with it. But yeah. So the relevant thing is the composition you start with roots specifically is not really important. That's just the point. Good observation.
Anyone else?
Have the actual polytopes have been studied by people in combinatorics with the polytopes?
The convex hull?
Yeah, exactly. So the actual convex hull.
I don't know of anybody who has done that.
Okay.
What were you asking or saying?
No, I'm asking. I'm not stating.
Okay. No, other than Cordian's article where he described these extremal points, I haven't really seen anything that speaks to the convex hull.
Okay.
Yeah.
So, conversely, if you give yourself this external point by a partition, and you construct polynomial that will have this set and H2.
If it satisfies the algorithm, maybe. I don't know. But it's if you take any arbitrary set, it's not going to be realizable. As in, it might be whichever one you chose, but it's not always going to. So I'm working with another student of Cordian's at the moment, where we try to determine some set of compositions if one of them always occurs, and we can kind of use this algorithm to just filter away some of the impossible arrangements, because every arrangement needs to satisfy the algorithm, but not everyone satisfies the algorithm. So yeah, so if you start off with a collection, it's not necessarily going to be a lesson. Yeah.
Any more questions, comments? We have time. Thank you again. The next talk is supposed to be online in 10 minutes, but I don't see the speaker on my video. Yeah, what's so okay, in 10 minutes we will continue.